Here we'll take a look at a couple of inequalities that involve absolute values. We can break these down similarly to the equalities. In the absolute value equalities, let's say 2x plus 3's absolute value was equal to 7, well, we would break out two possibilities, that either 2x plus 3 was already 7 or that 2x plus 3 was negative 7. In both cases, the absolute value of 2x plus 3 would have been equal to 7, and you can solve each of those individual equations on their own. Here, we're going to go through the same relative thought process, but we're not going to be looking for specific values. We're going to be looking for stretches of the number line where we would find values of x that make this equation true. And here's the way we can think about it. Let's do a number line. Put 0 in the middle. So there is this thing, which we happen to call 2x plus 3 at the moment. The absolute value of this thing is less than 7. That means this thing, this 2x plus 3, it couldn't have been 9, it couldn't have been negative 8, it couldn't have been 20 or negative 100, but it could have been 6 or 5 or 4 or negative 1 or negative 2. Any of these numbers, the absolute value of would give us something less than 7. And if you think about it, if the absolute value of 2x plus 3 is less than 7, that means that 2x plus 3 itself would be found somewhere between negative 7 and 7 on the number line. So the values of x for which the absolute value of 2x plus 3 is less than 7 are values of x which would make 2x plus 3 alone land between negative 7 and 7. And we can ask 2x plus 3, hey, 2x plus 3, what values of x put you between negative 7 and 7? By creating this compound inequality, which is the algebraic version of this picture, that 2x plus 3 is in between negative 7 and 7. We're not including negative 7 and 7. So open circles and no equals that equals part of the inequalities. We solve this for x the same way we would solve the expression without this thing on the left. You just make your decisions on how to scrape your way into the x. The first thing we have to do is scrape away the plus 3, and we do that by subtracting 3 everywhere. So when we subtract 3 from negative 7, we're down to negative 10. When we subtract it from the middle, we get 2x. That's the whole point. And when we subtract it from 7, we get 4. And then to scrape further into x, we have to remove the 2 by dividing by 2 everywhere, which means negative 5 is less than x is less than 2. And so this is the solution set. That means values of x between negative 5 and 2, when plugged into 2x plus 3, will give us something whose absolute value is less than 7. That's quite a chain of handing off of information, but it is what it is. We're looking for where absolute 2x plus 3 is less than 7. That means 2x plus 3 lives here. And in order for 2x plus 3 to live here, that means x alone has to live between negative 5 and 2. For the second example here, we have something very, very similar, except there's a little bit of clutter. We have to remove the plus 1 from the left-hand side first. And so we subtract 1 from both sides to generate this. And then thinking about a process similar to the above, if the absolute value of 2x plus 1 is less than or equal to 5, that means that 2x plus 1 itself, not with the absolute values, lived between minus 5 and 5. And this time, we will include those points and take all of that. And the algebraic way we describe that scenario, that 2x plus 1 needs to live between minus 5 and 5, is a compound inequality that looks like this. And then we can subtract 1 from everywhere, like so. And then we can divide by 2. And this is now the solution set to the inequality with the absolute value expression.